Hello, everyone. So first, before we get started with the lecture, I have a quick question for you. What is a pirate's favorite stats language? It's R. Yes, great jokes. In another life, I would have been a comedian, or in a later life. Anyway, enough of the bad jokes for today. Today we'll talk about custom functions in R. So one of the coolest things you can do with R, and as with most good programming languages, but certainly apart from SPSS, which I do not include in the category of good programming languages, is that you can create custom functions. And what custom functions allow you to do is to repeat certain procedures lets you repeat them very easily. So anytime that you find that you're doing the same thing over and over again in R, where you're repeating similar code, that's probably a good sign that you can use a custom function to dramatically simplify how much code you're using. And a function always has some input, which once it receives the input, performs some action. And as a result of that action, there's some output or result. And that output or result can either be a summary statistic of the data, or some transformation of the data, or even a plot. And we'll do some of those right now. So first off, let's create a function called myMean that replicates the mean function in R. Now, of course, there's no reason for us to do this because there already is a mean function in R, but this is a simple function, so it'll be easy to see how it works. So the first thing we do is give a name to our new function, which we call myMean, and I'm going to assign this. And the way you define a function is by using the function. Getting pretty, what was that movie? Where people kept going to sleep and then there was the people trying to steal their thoughts. Inception, yes. Function of a function, very Inception-like. Okay, so a function, then we define the inputs, which in this case, I'll just say the input is x, which is a vector. So input is x, just a vector of numbers. And before I do that, let me put an open curly brace. And then what do we want to do from x? Well, to calculate a mean, we first need to create the sum of it and divide it by the number of items, which in this case is length. And I'm going to assign this to a object called output. And that's pretty much it. So that's how you calculate a mean. And then the last thing I need to do is tell R to return this output. And then we can close the function brace. Now if I run this, then R has saved my function, but it hasn't done anything. And that's because I haven't called the function yet. So now if I go myMean, and I add a vector, I don't know, 1, 2, 3, 4, 5. This mean of this is 3. If I run this, I get 3. So it works. Let's do R norm of 10,000 from mean of 0. SD is 1. So the mean of this should be around 0. And that's what we get. So as you can see, it's really easy to define a function and assign it to something and then use it later. Now, in this case, this function is not so interesting because it replicated something that we already had, so it's a bit of a waste of time. So let's create an updated myMean that can automatically remove outliers from the data if I want to. And I'll show you what I mean by that. So we'll create a function that allows the user to say whether or not they want to remove outliers. If they do want to remove outliers, the function will automatically remove them, but if you want to keep them as well, that's fine too. So first we start the same way as before, myMean function of x. And then we also want to add one more input, and this will be a logical input called remove outliers. And to start off, I'm going to say equals false. And I'll explain what this means in a minute. But so now for this function, the user has to input both the data vector x and they have to say, using a true or false value, whether or not they want to remove outliers. And the reason I've included equals false is that when you're defining an input for a function, anytime you say equals something, then that will be the default value. So if the user doesn't specify what they want for the remove outliers, it'll automatically default to false. You can also do this with the data. So I can say my mean function x, and the default for x, if you don't even include any data, is just 10 samples from a standard normal distribution. Okay, so now let's open the brace here. And then first we want to define what happens if remove outliers is, let's start with if it's false. So we can do that by using if statement. So if remove outliers is false, then open brace. Then we'll say the output is just the mean of x. I could have repeated this before, but since we're doing a more complex function, I don't need to redefine a mean. I'll just use the existing value. So now, this is what the function will do if remove outliers is false. It'll assign the output to be just the mean of x. But now, if remove outliers is true, we need to tell the function what to do. So if we want to remove outliers, or let me put up here, what happens if remove outliers is true? Okay, so first we have to define what an outlier is. There's many ways to do this, but I'll just take one definition, which is that an outlier is a value greater than or more than 2 standard deviations away from the mean. So to calculate whether or not something is an outlier or not, we have to first figure out what the mean and standard deviation are of the original data. So I'll say original mean is mean of x, and original standard deviation is SD of x. And now we're going to create a logical vector that says whether or not each data point is an outlier. And the way we do this is by first defining the vector, which I'm going to call outlier.log for logical. And I'm going to assign this to the following logical condition. So first, if x is greater than original mean plus 2 times original standard deviation, so I'm going to define to say whether, if a value is greater than the original mean plus 2 standard deviations, then I'm going to say that's an outlier. So this is one way that it can be an outlier. Then I'll put this in parentheses. And then it can also, so this is the case where it's greater than the original mean plus 2 standard deviations. But now I want to include the condition where it's less than the original mean minus 2 standard deviations. So I'll just try to make this, I'm not so good at making things look pretty. Now that's better. So now for x values that are less than the original mean minus 2 standard deviations, then that will be an outlier as well. So this logical vector will tell me whether or not, or which values are outliers. And now I want to create a new x no out vec that only has non-outliers. And I can just use this by using indexing. So I can say x no out is x, but I'm only going to include values where outlier.log equals false. So for example, let's just say x is c of 1, 2, 1, 2, and then a big outlier. Now if I run this on x, so the first 4 should not be outliers, and the 5th should be an outlier. And it didn't like original mean. Oh yeah, because I have to redefine the mean and standard deviation. And now if I run this, it still didn't like that. What's the problem? X is fine. Original mean. Did I spell? Orig mean, not original. Orig mean, orig SD. Okay, now this should work. And it says that none of them are outliers. I definitely screwed something up here. So what's ridge? I think what happened was I made this such a huge outlier that it's making them all, it's making none of them look like outliers. Well, this is strange. Okay, well, let me just change x to see 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and make the next one 8. Okay, now that should definitely be an outlier. Okay, good. So I'm not exactly sure what I did wrong there. I think this was just so much of an outlier that it made the whole data kind of screwy. But now that I added lots of 1s and 2s, it's clear that this 8 is very different from the others. So in this case, it only says that the last one is an outlier. And now, if I take x and I take only the values where the outlier log is false, then again I screwed something up. It's probably because I didn't redefine it again. Okay. So now I run this again. Okay, so regular x value was this, including the 8, but now if I only include the indices where the outlier is false, then I get those. Okay, that's what I want. And now I can say that the new output is, for removing outliers is true, is just the mean of x, no out. And I can close that, and that should be the end of our function. So let me add a final closing brace for this one, and let me run this. And now I should have a new function called myMean. And what's also cool about RStudio, and I think it might do this in the regular R application as well, but it includes reminders of the different inputs even for your own custom functions. So in this case, let's say myMean of our normal 10, or let's say it's 100. So in this case, this should have an average value of around 0. And let's say remove outliers is, well, it doesn't matter in this case because there shouldn't be many outliers. But if I run this, then, oops, you know what I forgot to do? So after you run your function, or you define what you want it to do, you always have to tell it what you want it to return. So in this case, I need to return output. Because I didn't tell it to return the output, it didn't do anything when I ran this function here. So let me rerun this. And now if I run myMean, our norm, then that looks good. But now let's adjust this so that the data has an extreme outlier. So let's add a 10 here. So that 10 should be an outlier. Actually, let's make it 100, so it'll really affect the mean. Now, if I don't remove outliers, so remove outliers equals false, then I get an average of 0.905, which is pretty different from 0. That's because it's including this outlier. But now if I change it so remove outliers is true, and I rerun it, then you can see that now the mean is much closer to the 0. And that's because it's now ignoring this 100 value. And what's cool about myMean is that I can decide, it gives me flexibility to decide whether I want to remove outliers or not, which you don't have with the original mean function. Okay, so that's how we can easily remove outliers from data using a new myMean function. And what's also cool about custom functions is that you can then you can use your custom functions in other R functions. Exclamation point, because this is pretty cool. So for example, one function that I use a lot is tapply. And with tapply, you have some data that you're, some response data, and you have an index, and you have a function that you want to apply that function to the data over each index. So for example, if we look at the chick weight data, is chick weight? Yeah, it's capitalized. With chick weight, tapply weight, and I can analyze the weight quickly to show you how chick weight works. Chick weight is just a data set that's already in R. So I can say I want to analyze weight by different chicks, and I want the mean weight for each chick. And this gives me the mean for each chick in the data set. But there's no reason why we can't use our own custom functions here. So now, instead of using the mean, I can say my mean, And then if I want to add a specification for removing outliers, you can just add a comma and then include remove outliers is true. And R will know to pass this along to the function. And if I run this, probably the results aren't going to look so different. So yeah, the last one here was 1576. Before that was 149, 149, 1576. So I'm guessing in this case there weren't outliers, at least in for these two chicks, so the results are the same. But either way, you can put in your own custom functions into other R functions that take functions as arguments, which is really nice. Okay, so this is how we can create functions where we're calculating summary statistics based on certain specifications that we want. But another cool way to use custom functions is to create plots. So a lot of the time when you make plots, maybe you don't like the default way that R creates plots. Maybe, so let me create. If I just run this, then maybe you don't like that in general the circles have a white border or background. Maybe you always like to have it red, and maybe you always like to do any kinds of things that, of course, you can specify here, but maybe you want to create a custom function that will automatically do all these things for you. And this is a good time to use a custom function for that. So let's create a custom histogram function with new features, not in the base function. So what I want to do is I want to add a few inputs. So the first I'm going to call add median, and this will tell R whether or not you want to add a solid vertical line at the median of the data. And then an add mean, which add at the mean. And another one might be to add a legend. And in this legend, we want to include a description of the median and mean lines. Add legend with description of median, mean lines. Okay, so let me add a little bit more space. And first is we want to define what the name of the function is. So in this case, it'll be myHist. And it'll be a function that takes a few arguments. It will take x, which is the data, and it will take all these logical values. So add median, and I'm going to set the default to this to true. Add mean, again, set the default to true. Add legend, maybe I'll make the default false, because maybe I don't always want legends in there, but I want the option to include it later if I want to. So to do this, we want to start by just creating a histogram. So it can be nice to test your function as you're writing it. So I'll just say x is our norm 100, and let's just make sure that this works. So hist x, yeah, that looks good. And now we want to set all the conditions. So if add median is true, then I want to add a line, add line vertical is median of x. Now if add mean is true, now actually the way logical values work, I don't need to say equals true. I can just say if add mean, because that's either true or false. But I like to include the full description just because it helps me see exactly what I'm doing. So if add mean, then add line. Vertical is mean of x. And actually, let's make these lines look a bit different so we can distinguish between the median and mean. So let's make the median, or sorry, the mean have a LTY or L type of 2. And to show you how that will look, L type of 2, line type of 2 is a dash line. And we'll leave this L type 1, but I don't know, maybe we'll make them both a bit bigger. Now in this case, I'm going to hard code the width to be 3 for each line. But you could include line width as an input to your function, which will then pass the line widths down to the plots. So anything I do here, I can also further customize it as another input to the function. But for this case, I'll keep it simple and just say it's always going to be 3. And now if add legend, create an open brace, and add a legend, and I'm going to put this in the top right. Again, if I wanted this to be an input, I could just add another like location of legend as another input, and then pass it along to here. And yeah, so it'll be the median, the mean, and the L widths, I'll say just 3 and 3, and line types is 1 and 2. Close this, and now I can close the function, and this all looks good to me, so hopefully no errors. Looks good. Okay, now let me just clear this plotting space. And now let's try our new custom histogram. So my hist, and let's say our normal of 10. And it worked. So you can see that even though I didn't specify add median, add mean, and add legend, because I didn't specify it, I went to the defaults, which in this case included the median and the mean line. But it didn't include the legend because I didn't tell it to be true. So I can add that by saying add legend is true. Now if I run it, it automatically includes the legend in my plot. So you can see that if you're running, or if you're creating many of these histograms, maybe for different participants in a study, or different data from different studies, it's a bit of a pain to have to constantly, after each histogram, write abline v is mean, abline v is median, and to do this every single time. So instead now I can just create my custom histogram and just run this single line of code for each analysis instead of having to type all this each time. Okay, so that's creating a univariate plot, but now let's try a custom histogram or scatter plot with added reference lines and what most people ask what you can do for a scatter plot when they're first introduced to R, which is and added regression line. So we're going to have a few different inputs here. We'll have add mean, which adds a reference line for the mean of both the x and y axes. Add regression, which adds a regression line. And then I'm going to make this a bit fancier. I'm going to say if the p-value for the slope of the regression line is less than 0.05, then make the line red, otherwise black. And the next thing I want to do is add a conclusion. So if someone wants a conclusion, then I'm going to add a sentence, so actual text, to the top of the graph with the main conclusions. Okay, so that's a bit confusing. We'll see what that all means in a second. So I'm going to call this function myScatter, and that'll be a function of an x, which I'll set a default, all norm 100. I'll set a y, which again, as a default, just 100 samples from standard normal. And now I'll add my custom inputs. So hold on, let me scroll down. So add mean, I'll default it to true. Add regression, default to true. And add conclusions, why not? I don't know, I'll set it to false just so we can play around with it. Okay, now I create open brace. And the first thing I want to do is create the plot. So I'll create a plot of x, y, and I like PCH21, BG is gray, 0.5, alpha equals 0.5. But again, you can also create the PCH as another input to the scatter function. So let's quickly just see how this is looking so I can test it as I'm going. So first I need to define x and y. Now if I run this plot, okay, this looks like a good starting plot for me. And now I can go through the different criteria. So if add mean is true, then I need to add reference lines for the means. So I can do that with abline h. So the horizontal line for y will be the mean of y, and I'll set the color as gray of 0.5. And then I can add the line for the x-axis. So vertical of the mean of x. So wherever the mean should be around here. Let's add another line in. What the heck, why not just make the line type as 2 for both of these. Okay, so now we've got the add mean function done. Next one's going to be a bit trickier, adding regression, but not too hard. So if add regression is true, then what we want to do is, actually, you know what? Do I want to start with the regression or do I want to start with the conclusions? No, I think I want to start with the conclusions. So if add conclusions is true, then the first thing I want to do is calculate a test of the correlation between these two variables. So I'll call it a c-test, and I'll assign this to core.test of xy. If you haven't seen this before, so if I run this, then you can see if I just run core test xy, I get the result of the test of correlation, and I can assign it to the c-test object by using our assignment operator. The next thing I want to do is extract the coefficient from this. So coefficient is c-test, and the value of that is estimate, which if I run this, you can see that for this example was -0.08. And finally, we want to get a p-value, and that's going to be in c-test. I think it's just called, p-value. If I run this and look at the results, then you see the p-value is 0.387, so non-significant. Okay, now we want to create a conclusion sentence based on this. So first I'll call this conclusion. I'll just call it conclusion actually, and I'll assign this. And the way that you can combine characters and objects like we want to do here is by using the paste command. And I'll say, it says note, the correlation coefficient is space, and then I add the coefficient, but I'll round. Actually, you know what, I'll just round it up here. That'll make it a bit easier, because otherwise we don't want tons of significant digits here. And I'll round the p-value as well. So, note the correlation coefficient is coefficient, and it will take this value from our test that we just did. And then I'm going to add a period, and then I'm going to add this /n, which just creates a new line. You'll see what this does later. So they won't actually print this in the output, but it'll just make the result look nicer. And then I want to say actually, you know what? I'm just going to skip that part. So I'm just going to say, yeah, it is that. Okay. Good. So next, I want to add text to the top of the plot that will have this conclusion. So the way you do that is by using mtext, which you can see first you include the text, which in this case is conclusion, and you have to say where it's going to go. It either goes 1, 2, 3, or 4, and I want it in 3. Side equals 3. Okay, then I'll close that. All right, now finally let's do the regression command. So if add regression is true, then the first thing we want to do is calculate the regression line, and I'll assign this to an object called model. So I'll say model is linear model of y tilde x. If I run this, I get that, and you can just quickly see if you're not used to this command. This gives you the intercept and the slope for the line, and you can also get the p-value as well, which we'll get in a second. So the p-value will assign to the way you get it is from first writing an ANOVA on model, and then from that you have to get the PR greater than F. There might be a simpler way to do this, and then you have to get the first one. So if I just show you the ANOVA of the model, then this is the ANOVA table, and we want to extract this p-value. And you can get that from, yeah, that's what this element is called, if that's how you name it. Then if I run all this, then I'm left with just the p-value, and that's all I want. So that's how you extract the p-value from it. And now I want to say we need two different conditions based on the p-value, because again, I said that I wanted the regression line to be red if the p-value is less than 0.05, and otherwise it's black. So how do we do that? Well, we say if p-value is less than or equal to 0.05, then we want to say that the regression line color, and that's a new object that I call, should be red. But if the p-value is greater than 0.05, then I make it black. And then we just need to add the line. So do this by abline model. I'll make the line type 2, the width I'll make it heavy, and then for color I make it the reg line color, which is dependent on whether or not the p-value is less than 0.05 or greater than 0.05. So let's just make sure this works, and then now I'll add the line to the plot, and it's black in this case because again our p-value is less than, or was greater than 0.05. Okay, oh, and also to see what this looks like, let's run ctest coefficient p-value conclusion, and this is how our conclusion is going to look. So it'll automatically put up the correlation coefficient. If we want to get a bit fancier, we can also say whether or not it's significantly different from 0 by, again, looking at the p-value and then creating new conditions. Okay, so add regression line is done, and I think that should just about do it. So that'll close the function. Okay, so let's run this. Hopefully no errors, always good. All right, so let's begin by generating some data. So let's say x is our norm of 100, and now let's create some uncorrelated data. So I'll call that x or y uncore, and that'll just be another random sample from a normal distribution. Should not be correlated with x, but of course by chance it could be. We'll see what happens. And I'll say y correlated is x plus r norm 100, mean of 0, SD of 0.01. So y correlated is just x, and then I'm going to add a little bit of random noise. Run these three. And now let's try running my scatter. And let's do it on x and y.uncore. And let's make sure that we include the values we want. So add mean, I think that defaults to true, but let's just say it's true. Add regression, yeah, let's do that. And add conclusions, sure, why not? Now if I run this, then you see that it has just generated our new plot, and the correlation coefficient was 0.08, not very big, and we get the black line that we want. And we also have these mean reference lines here. But now let's run this again, but now instead of the uncorrelated data, let's do it on the correlated data. And just to see how these inputs work, let's change the regression line to false and add mean to false. So now when I run this, it says the correlation coefficient is 1, which as we can see, I added almost no noise. Actually, this is so little noise that it's almost not interesting. So let me redo this. Let me run it again. Still, let's add standard deviation of 1. So at least we get some noise in there. Okay, that looks better. So correlation coefficient is still high, but now if we want to add the regression line, all we have to do is change the input to true. And if I run this, now we've got the regression line. And I can make a little dance by just running this over and over again. And each time I run the plot, it's generating new data, adding the regression line, which in this case is pretty much always significant because I added so little error. Maybe if I make it a bit bigger, then every once in a while we'll get some that aren't significant. No, still always significant. Let's make this 5. Now these shouldn't be so correlated. Yep, so now we got one that's not significant, one that is, one that's not, one that is. Hey, I think I hit it just about 50%. Yeah, so you can see how this works. Okay, so that's how you can create customized plots in R. So all this original code for creating the function is definitely a bit long, so you have to define all these conditions. But once you've done that, it's so easy to create your own plots that look just the way you want without having to constantly redefine all these different variables. Now, one thing to keep in mind is that R will not save your custom functions, which of course sounds like a big issue, because if I had to retype all these custom functions every time I want to run an analysis, that would be a bit of a pain. But there's a way around this that makes it much easier. So what I can do is save all of my custom functions in one file. So I have one big R file that's just called Nathaniel's custom R functions, and I have all my functions defined, and then I save that file, and then what you can do is use the source command to automatically load all of your custom functions in a file. So first you want to, well, the way you can do that is just by writing source file equals set the directory, so maybe it's, I don't know, users Nathaniel, maybe it's on my desktop, and then if my custom functions file is called custom functions.r, then if I run this command at the top of any new data file, so let's say I took this, and then I want to create some new data, so new analysis, it starts off, custom functions aren't there, but if I just run source of, and I specify the file, then it will automatically run that entire file and load up all my custom functions. So now custom functions are back, and I can start using them again. And then I can start using my scatter again. Can't find the function myScatter. That's because I spelled it wrong. And because I have, again, I have default values for everything, I can just keep running this over and over again. Yep. So I recommend that everyone create their own file which they keep all their custom functions in, and then anytime they start a new analysis or document, just source that file in and you've got them all back. And that's an overview of how to use custom functions in R.